So my name is Padraig Dunne. I'm head of the School of Physics at the moment, and I'm just going to spend about 10 minutes talking about electronics and light for electronics. And I suppose the iPhone is a perfect example of this as I set my timer, that here we have a set of electronics that give you light. So I've started myself on 10 minutes. And electronics give light bulb, all sorts of stuff, but in order to make electronics, you have to use light. And this has been a remarkable process over the last, say, 40 years, actually 50 years. In 1965 is when the idea of making microelectronics and shrinking them and squeezing the most value out of silicon started. And here's a silicon wafer. It's an old one, that's why I have it. They used to make silicon chips on wafers this size. So I put it here, and I'll just turn on this for a second, just to show you that it's what it looks like, right? So here it is, and I'll have to tilt it so you can see it a bit better. And then if we zoom in on it, you can see there's lots of little microcircuits in focus. And inside those microcircuits, there's loads of little details. Right, so that's what's on. And in the computer processing manufacturing these days, so out in Intel and Leaksley, for example, they make them on wafers this size, and everything is way smaller, as I'll explain. But that smallness comes from the ability to manipulate light and create light on a really remarkable scale. So here's a nice internet picture of the same thing. So Moore's Law, Gordon Moore, 1965, founder of Intel, or co-founder of Intel, multi-billionaire, donor to universities, all of that. He wrote an article in 1965, the same week that I was born, and he said that roughly what's going to happen is every few years, 1 year, year and a half, 2 years, things are going to shrink by a factor of 2. That's what I reckon is going to happen. And this is how we're going to do it, more or less. We're going to make things smaller and smaller and package them tighter and tighter and sell them cheaper and cheaper. And as you can see here, these feature sizes started off in 1985 on this graph, so 20 years after Moore, they were about 1 micron. And by 2015, they're about 15 nanometers. Now that sounds great, but what's a nanometer? So if I take one of the hairs out of my head, actually I've taken 2 there, right? That's a high proportion of them. This hair, I can't show you, this hair is 80,000 nanometers across, or maybe 70,000, depending on how recently I washed it. 70,000 nanometers across this hair. And the features inside the chips that you're looking at here are 15 nanometers at the smallest. And they're made on wafers the size of a large dinner plate. And when those factories are running properly, every hour, a proper running factory or functioning tool will make about 30 million euros worth of wafers every hour when it's up and running. One tool in a process. So you're talking serious investment based on this Moore's Law. And Moore's Law has taken the entire semiconductor industry and driven it to this state where they're lockstepped into this, divide by 2 every couple of years, the cost goes down by 2. This processor has more power than what sent things to the moon, many times more. This probably has more power than the Irish Central Bank did in 1990, this processor. It's unbelievable. So how do they do it? So the basic process is called lithography, which is, I better just check my time. Lithography is making shadows, printing. Originally it came from this printing on stone, and you would make a pattern in stone and rub something over it and stick the thing down and get the pattern. Nowadays you have a mask and a wafer, and the light shines through the mask and reproduces the pattern on the wafer. And that's fine. We're all used to this idea. I put my hand up here, we get a shadow of my hand. How difficult can it be? So in the silicon process, somebody takes a wafer like this, puts it into a machine, and they flatten off the silicon first of all. Now don't forget, the things have to be a nanometer, 15 nanometers in size. So they have to flatten this surface down to a bit better than a nanometer across this dinner plate. Then they coat it with the photoresist, which is that red layer on top. And then they shine light through a mask. So these black bits block the light, and the clear bits let the light through. And where the shadow is cast, you can then let these acids, or ions, or whatever it is, start etching into the silicon, and you end up with features in the silicon. And that's the basic lithography process. So you just cast a shadow, simple enough, and where the light shines, you break the bonds, and where the light doesn't shine, you don't break the bonds, and then you wash the thing through with chemicals, and it ends up getting to look like this. And then maybe what you do is you make this P-type and this N-type, and you make a transistor, and you have your features on your computer chips. But we all think about light casting a shadow like this, just going through the slits, and it's a straight line. So surely it's easy to make a pattern over here where the light has just gone in straight lines, because we know that that's what light does. But when you get to the small scale, light does this. It bends out around the edges of the aperture, it diffracts. So instead of getting a nice, neat shadow cast on the right-hand side, you end up with a blur, a blob. Not a very useful feature if you're trying to make the electrons in your semiconductor behave themselves so that your computer program doesn't crash. So instead we get diffraction. So the image of a nice, simple slit appears to be this blob with another blob and another blob. So we'd call this a constructive, a bright fringe, a dark fringe, a bright fringe, and so on. And you can see that that wouldn't be very good if you're trying to etch straight lines and corners and dots onto this. So what do? Just to illustrate the point, you're used to the idea of a light bulb, the light's going through the mask, through the wafer, but instead you end up possibly with this. It turns out the smaller you make the feature in the mask, the more the light spreads out. And therefore, your process of miniaturizing and miniaturizing and miniaturizing gets more and more difficult as you get smaller and smaller because the diffraction gets bigger and bigger. So are you familiar with this idea of the spectrum? In red light here, I've talked about it, blue light over here, ultraviolet over here, infrared down there, radio even further, X-rays even further. Blue light carries more energy, but it's described by having a shorter wavelength. So it suffers less from diffraction than red light does. Red light causes more significant diffraction. So red light spreads out more going through the mask and makes a bigger blob on the wafer. So the very first thing the semiconductor processors did was they went from a red line of a mercury lamp to a blue line, and then they went down to an ultraviolet line, and then they ran out of colors emitted by the mercury lamp. And there was a sort of a technological challenge there. If we take the spectrum and squash the visible bit down to here, and this is a log scale, if we go out across down to the right-hand side, we're going into higher energy, shorter wavelength. And down here around the sort of soft X-ray, the 1 nanometer region, between 10 and 1 nanometers, we're in what's called the soft X-rays. That was thought about for a while, but eventually the industry settled on this extreme ultraviolet region as being the place where they would make their next technological revolution in terms of making light go through slits. And you see there the wavelength of that light, it's up on the top, it's about 13.5 nanometers. And the features you're trying to write are about 15 or 10 nanometers. So it seems that these two things are of the same order, so that makes it kind of easy to write small features with this light. So that sounds grand. But we're used to light traveling through lenses and all sorts of media like water and air. But soft X-rays and extreme ultraviolet light is even worse than soft X-rays. Extreme ultraviolet light doesn't go through very many things. So you have to, instead of making lenses, you have to use mirrors. And the reason we picked 13.5 nanometers, we being the global industry and people who do research, is because there are very good mirrors at 13.5 nanometers. So that's fine. Okay, so then we just need a light bulb that'll work at 13.5 nanometers. Will we try this? No, that's not going to work. This isn't going to work. That's not going to work. What will actually give you the light at 13.5 nanometers is the question. Now, don't forget, a nanometer is 80,000 times narrower than my hair, or 70,000, thereabouts. So 13 nanometer light is incredibly highly energetic. It's bad for you, but it's very energetic and it's very short wavelength. But it works for the semiconductor business. So what you've got on the left-hand side is your typical visible light bulb. It's got an incandescent, old-fashioned light bulb. It's got a filament in it made of tungsten, which gets really hot. Have I got 3 minutes? Yeah. Very hot, but not really. What we do and what the industry has moved to is a light source made by focusing a laser onto a solid target or a liquid target or a droplet target, which forms a plasma at about 1,000,000 degrees, so much closer to the temperature inside the sun and inside a star, and it emits extreme ultraviolet light. And what you've got to do then in this kind of, so the goal of the research is to make this light bulb, the plasma light bulb, as cheap to make as possible, as reliable to run as possible, so that you can ship them out to Intel or whoever. It's only going to be a few companies left, Intel, Samsung, TMC, Global Foundries. There aren't many companies left. The dearer these things get, the smaller the number of companies can afford it. So the big companies buy up the small companies. It's only 2 or 3. And they make chips for everybody else. But you've got to have this laser plasma sitting in a vacuum, because X-rays get absorbed by light, running to give you enough energy to put through 100 wafers per hour. 100 dinner plates with these chips per hour. And that means that you need to, the ultraviolet light is only going to be about 250 watts, which doesn't sound like a lot, but to get that, you need to put into the machine about 200,000 watts. of energy. So they're going to be expensive on electricity. And this is what the machine might look like. So you have your laser over on the left-hand side, which is an idealistic diagram. You have a droplets target firing little tiny 30 micron tin drops into a vacuum. Each one gets hit by a combination of lasers, which makes it into a light source, extreme ultraviolet light source. And that light then goes through and bounces off a whole load of mirrors, because you can't use lenses, and your wafer sits above that arrow on the platform. And that's me, my timer done. That's my 10 minutes, or 11. The wafer sits on that platform and moves around the place to better than a nanometer precision on the size of a dinner plate. And the boys etch the wafer, and then they send it through, and the girls and the boys, I should say, really, because it is a male-female environment in Intel and other places. They etch, step the thing through, do about 100 processes to make their chips. And this is what it looks like with the scale man. This is, ASML is a company in Holland that is the world leader in providing these tools, and may only be the only one for a few years until Nikon or somebody gets back into it. There's the kind of a man-sized thing there. You can see the lasers would be underneath the floor, and all the wafer handling and the optics are all there. So in order to make these new generation of electronics, you need to have an extreme ultraviolet light source driven by a laser. And all of the research for that has come out initially from the universities and then moved kind of into a competitive era. It was pre-competitive in the universities. Now it's moved into the industrial regions, and it's more kind of competitive engineering, research and design at this stage. About 10 of these machines have been shipped around the world, and none of them is deployed in actual manufacturing yet. They're all deployed in process improvement and that sort of stuff. So I suppose what you'd say is, in the year of light, probably by the end of the year of light, somewhere, somebody in the world will start making one feature or one layer in these wafers with extreme ultraviolet light. And I should stop there and say thank you. And that's us on the hills when we aren't making extreme ultraviolet light. So thanks very much.